Hi everyone, myself Harishankar from the Gate Coach. Today we are going to discuss about the newly added topic in Gate called transport property. So this topic, transport properties, are added in your fluid mechanics syllabus. So let us see, right, what is the meaning of transport property and what are the transport properties. So first of all, transport properties characterize the response of a fluid with respect to its changes in its temperature, speed of flow or composition, right? Speed of flow or composition. Once again, these properties characterize the response of a fluid, right? So we are interested in the response of a fluid, right? With respect to the changes in its temperature, speed of flow or composition. Now, the question is, what is transport process, right? What are the transport processes, right? So first of all, right, transport processes are where mass, momentum or energy, right, mass, momentum or energy are transported from one region to another region under the influence of what? Under the influence of these three things, right? Under the influence of these three things, where mass is transported according to this, momentum is transported according to this, energy transported according to this, right? So this is what we are going to discuss. Now, what are the three transport property we have? We have three transport property. The first property is our thermal conductivity, which is related to our energy transfer or heat transfer. Viscosity, right, that is our dynamic viscosity, which is related to momentum transfer. And we have what? Diffusivity, mass diffusivity, which is related to our mass transfer. Right? I hope you are okay with the three transport properties we have. What is that? That is, one is thermal conductivity, viscosity, and our diffusivity, right? Our diffusivity. Now, for example, if you take thermal conductivity, right? If you take thermal conductivity, what is the meaning of thermal conductivity? Right? It is actually describing, thermal conductivity is actually describing what? How quickly it is possible to heat a fluid in a pipe. Right, simple. How quickly we can, right? How quickly we can heat a particular fluid in a pipe. This is what the meaning of thermal conductivity, right? So same way we are going to discuss what thermal conductivity, viscosity, and diffusivity, right? Individually. Now we are going to explain the three transport processes or our transport properties in detail. Now, what is our first transport process? Okay, so you can see here, diffusion. We consider the mass transfer first. Diffusion. Matter is transferring, right, or our mass is transferring from what? From high concentration to low concentration. Now, what is our second transport process? Second transport process, we are taking our heat transfer or thermal conduction, right? Heat transfer or thermal conduction, where the thermal energy or our energy is transported, right? Our energy is transported from high temperature to low temperature, right? I hope it is clear, right? So these three things. The third one is what? Viscous momentum flow, right? In that, what is transferring? Momentum is transferring from high velocity to low velocity. Now, these three processes are individually discussed in our what? Three subjects, right? Mass transfer, heat transfer, and in our fluid mechanics. So we are already, right, we are already discussed what these three processes in detail, right? So but what we are going to do here is what? We are just going to take some result, so that we will be able to explain what our three transport properties separately. That is thermal conductivity, viscosity, and diffusivity. Now you can see, right, what is the general equation, right? What is the general equation for flux or rate of flow or flux? What is the general equation? General equation is flux is, right? So whatever thing is transported, right, that flux is proportional to rate of change of some property with distance, right? Rate of change of some property with distance. I was discussing about flux. So what is the meaning of flux? Flux is our rate of migration of a property, right? Rate of migration of a property. So what should be the unit? Whichever quantity is transported per area per time, right? So per area per time. So this is our flux, right? This is our flux. So just now I have just written this, right? So your flux is proportional to what, right? Our flux is proportional to, always it will be proportional to first derivative of some property. Right, first derivative of some property. So in our three cases, we are going to discuss which is that property. Right, in our three cases, we are going to discuss which is that property. I hope it is clear. Now, first of all, mass flux, right? Mass flux, which is the thing or which is the quantity that is transferring? It is our moles, right? Our moles are getting transferred. So the unit of mass flux is what? Mole per meter square second. Right? Mole per meter square second. Now you can see the equation. So it was actually our mass flux is proportional to concentration gradient, right? Concentration gradient, that is higher concentration to lower concentration. Our constant of proportionality is our diffusivity. What is the unit of mass diffusivity? DAB, meter square per second. So this is our mass diffusivity. Now when you come back to the second stage, what is our second thing? Heat flux. In heat transfer, what is transferred? The energy is transferred. That's why joule per meter square second, right? I hope it is clear. Joule per meter square second. Now, joule per second is what? Watt, right? So the unit can also be equal to, what is your same unit? Watt per meter square, right? Watt per meter square. I hope it is clear. Now, what is the proportionality? Right? Proportionality is our thermal conductivity, right? Here it is our thermal conductivity. Now, when you come back to momentum flux, right, or our shear stress, it is equal to what? It is proportional to the velocity gradient. Our constant of proportionality is our viscosity. Now, what is the quantity which is transferring here? You can see the numerator, kg into meter per second. This is our momentum, right? Momentum per area per second, right? So it's about our momentum transfer. Now, what is the normal unit of tau? Tau, the unit is what? Newton per meter square, right? So Newton per meter square. So we can write this unit like this so that we will have a general equation, right? That is quantity divided by meter square per second. So this is about what? This is about our three transport properties, right? This is about our three transport property. Here we are having what? Mass transfer, energy transfer, and finally we are having momentum transfer. Now, when you compare these three equations, right? When you compare these three equations, if you see the transport properties units are different, right? Units are different. So we are interested to write, right? We are interested to convert the transport properties in terms of the same unit so that it will be easier to compare these three properties, right? So we are moving to our next topic. Now we were discussing about mass diffusivity, so I hope you remember J is equal to minus dAB into dCA by dZ, where our dAB is what? dAB is our mass diffusivity. So we already told, right? We already told this is in the form of what? Concentration gradient, right? We want to write in terms of concentration gradient. So what I am going to do is, right? You can see here, instead of my thermal conductivity, I am writing in terms of thermal diffusivity alpha, right? If I write this equation in terms of thermal diffusivity, the only change I have is, right, instead of this, in my bracket, you will be having rho Cp into T, right? Rho Cp into T, right? Now you can see this is in the form of what? This is in the form of the first equation, right? This is in the form of the first equation. Now, the third equation for viscosity, I am changing this equation as, right? You can see here I am changing the equation as in terms of kinematic viscosity, right? In terms of our kinematic viscosity or momentum diffusivity. So I am writing this equation as d by dz of rho into velocity. Clear? Right, rho into velocity. I hope it is clear. So you can see here we have written three equations now, right? We have written three equations now. Now if you check the units, right, so I am going to discuss about the units now. If you check the unit of dAB is in meter square per second. Now what is the unit of alpha? What is the equation for alpha? Right, what is the equation for alpha? Equation for alpha is K divided by rho Cp. Right, K divided by rho Cp. What is the equation of kinematic viscosity? Viscosity divided by density. Now, I hope you remember the unit of thermal diffusivity. Thermal diffusivity unit is meter square per second. What is the unit of kinematic viscosity? Meter square per second. Now we can say what, right? Now we can say we have three terms which are having the same unit. So we can say these three are analogous to each other, right? So very simple. So you can see, so this can be considered as what? Your thermal concentration of energy, right? Your thermal concentration of energy. And this can be termed as what? This can be your momentum concentration, right? So this is what? This is the general mass concentration, right? This is your normal concentration. So we have written all the equation in terms of concentration gradient. Now we are getting what? dAB is your mass diffusivity, alpha is your thermal diffusivity, and nu, that is our kinematic viscosity. It can be called as what? Your momentum diffusivity, right? So these are the three diffusivity we have. Right, now what is the meaning of thermal diffusivity? Right, it is the ability of a material to diffuse heat. Physical significance of these three terms, right? What is the physical significance? The meaning is very simple. If you have a material of higher value of alpha, heat diffusion through the material will be very, very high. Right, heat diffusion through the material will be very, very high. Same way, what is the meaning of our kinematic viscosity or momentum diffusivity? I hope you remember. What is the kinematic viscosity of water? Right, kinematic viscosity of water is 1 centistokes. Right, I hope you know how to convert it. Now, same way, what is the kinematic viscosity of air? Kinematic viscosity of air is 15 centistokes. So the meaning is what? Right, so meaning is you can see the momentum transfer, right? You can see the momentum transfer or transport of momentum. You can compare it with water and air, right? In air, the transport of momentum is fast compared to the momentum transfer in water, right? So you can see air is 15 times, right? So the value of kinematic viscosity of air is 15 times that of water. Right, so which will transport momentum faster? Our air will transport momentum faster compared to the water. So this is our thermal diffusivity or momentum diffusivity or mass diffusivity, the comparison. Right, I hope you understood this. Now, based on this, you are having lot of dimensionless numbers. I hope you remember. Right, I hope. Now, based on this, you are having what? 3 different numbers. Right, so I hope you remember. What is your Prandtl number? What is this? What is this? There are 3 numbers are there. I hope you remember. What is your Prandtl number? Prandtl number is your momentum diffusivity divided by alpha. You have the equation. What is Prandtl number? Cp mu divided by K. Same way. What is the second number? Lewis number. Right? Second number, Lewis number is your thermal diffusivity divided by our mass diffusivity. Right, I hope you remember. And the last number you can see here, this will be what? Right, so we have already discussed the first 2. So obviously the third one will be your momentum diffusivity divided by mass diffusivity. So these are the 3 dimensionless numbers we have. Right, I hope you remember this. Since we discussed about our viscosity, so we will see, since this transport properties comes under our fluid mechanics syllabus, we will just see the type of questions, right? Type of questions in fluid mechanics. Right, the major type of question in fluid mechanics is like this. I hope you remember the flow, pipe flow, right? Pipe flow or laminar flow in a pipe. So what are the major type of question you will get, right? So there is only one type of question in our laminar flow, right? So if you see the logical question, right? So what is the type of question we encounter in our gate? It is very simple. You can see here. So we will consider a pipe, right? So they will give you a pipe, right? So for example, consider a laminar flow in a pipe, right? So they will give you the diameter of the pipe. First of all, diameter of the pipe will be given to you, right? So sometimes they will give you 100-meter long pipe, right? It is a 100-meter long pipe, and right, so we need to send what? We need to send, for example, 100 liter of water in 1 minute. This is your flow rate in the pipe, right? This is your flow rate in the pipe. What is our objective? Our objective is to send 100 liter per minute of water, right? 100 liter per minute of water through a 5 centimeter diameter pipe, right? 5 centimeter diameter pipe or tube, right? So 5 centimeter diameter pipe of the tube. It is a 100-meter long pipe. Now, for this, right? For this, the pumping power we require is, right? For this, the pumping power we require is 16 horsepower, right? So this is the pumping power we require, right? This is the pumping power we require, and they have given it as what? They will give you as laminar flow. Right, they will give you as laminar flow. Now the question to you is, everything is given in this question, right? Everything is given in this question. They have given, there is a 100-meter long pipe. We need to send in 1 minute, we need to send 100 liter of water. Diameter is 5 centimeter. Everything is given. For that, how much pumping power we need to supply? We need to supply 16 horsepower. Now the question to you will be in gate, right? So you have seen the previous question, right? Previous year question. So this was a previous year gate question, right? So their question is very simple. They are going to double the diameter of the pipe. That is, initially your diameter of the pipe was 5 centimeter. Now the diameter of the pipe is 10 centimeter. They are not changing. They are not changing anything. Right? They have just changed the diameter of the pipe. The length of the pipe is same 100 meter. Right? Length of the pipe is same 100 meters. Same water is to be sent. Now, what is the flow rate of water? Now we want to send the same 100 liter per minute of water. Now the question to you is, determine the pumping power, right? How much pumping power we should supply, right? For the second case. Clear? So this will be your general question, right? So this was one of your previous year question. Now, first of all, how to calculate this? Now, what is the equations you have? Right, it is a laminar flow is given. So, for any flow, right? So, what is the pumping power equation? I hope you have the equation for pumping power. Pumping power is equal to Q into your delta P. What is delta P? Delta P is your pressure drop. What is the meaning of pressure drop? It is the pressure loss from point 1 to 2. When you have a flow from point 1 to point 2, what is the energy loss? That is your delta P. Right, that is your delta P. Now we can see here, for both pipe, right, your length is same, right, your flow rate is same. So since the flow rate is same for both cases, your pumping power will be what? Your pumping power will be, right, your pumping power will be directly proportional to the pressure drop. This is the first thing you need to understand. Your pumping power will be directly proportional to the pressure drop. Why? Because here also we need to send what? 100 liter. Here also we need to send 100 liter. So Q is a constant for both pipes. Right? Now we are interested to find what? What is the pumping power in the second case? How can we find this? We can write like this. Pumping power in the second question, right, divided by pumping power in the first question is equal to delta P2 divided by delta P1. Clear? Easy. Right? That is. Now, what is the equation for pressure drop in a laminar flow? I hope you remember. What is the equation for pressure drop in a laminar flow? If I write in terms of flow rate, my Hagen-Pauli equation is 128 mu QL divided by pi d power 4. This is the equation for pressure drop. What is the meaning of this equation? What is the physical meaning of this equation? When you transport water through a pipe of diameter d and length of this, right, length L. If you want to transport water at a flow rate of this, you will experience this much pressure drop. Right, you will experience this much pressure drop. What is the reason for this pressure drop? The reason is viscosity, your transport property. Right, what is the reason for this pressure drop? Reason is your transport property, viscosity. Now my question is, if it is an ideal fluid, what will be the pressure drop? If it is an ideal fluid, what is the meaning? Viscosity is 0, your transport property, viscosity is 0. So pressure drop will be 0. Right, there is no pressure drop if it is an ideal fluid. Now, but it is not an ideal fluid, so you have a viscosity, right? You have a viscosity for water. Now we are interested to find what is delta P2 by delta P1. Now we are going to compare what are the cases, right? What are the things that is changing? What are the properties that is changing from case 1 to case 2? If you see, 128 is a constant. Mu, what is mu? Water is flowing through both pipes, right? Water is flowing through both pipes. So viscosity is constant. 128 is constant. Viscosity is constant. Length of the pipe is 100 meter. Length is also constant. And your flow rate is also constant. So 128 mu QL and pi, everything is constant. So what is your proportionality? Delta P is proportional to 1 by d power 4. Very simple. Right? 1 by d power 4. Right? 1 by d power 4. Now the meaning is what? Your pressure drop is proportional to 1 by d power 4. Now what is happening to your diameter? Diameter is doubling. Right? Your diameter is doubling. So what will happen to delta P2 by P1? Just substitute. Right? Just substitute. You will be getting what? You will be getting. Right? You will be getting, if you substitute this. How can you convert this? It's very easy. That is, what will be your delta P2 divided by delta P1? It will be your D1 divided by D2 power 4. Right? D1 by D2 power 4. What is your diameter? First diameter? 5. D1 is 5 centimeter. D2 is 10 centimeter. It is double. So it will be what? It will be 1 by 2 power 4. Right? 1 by 2 power 4. I hope it will be clear. 5 divided by 10. So it will be what? It will be, if I substitute this will be 1 divided by 16. Right? It will be 1 divided by 16. So if I substitute pumping power equation here, 1 divided by 16. 1 divided by 16. What is the pumping power for the first case? 16 horsepower. Substitute. And what is your pumping power for the second pipe? Your second pipe pumping power is, it will be 16 by 16, 1 horsepower. Now you can see what is the change, right? What is the change? What have you calculated? For the first pipe you require 16 horsepower. For the second pipe you require what? 1 horsepower. Now, when you double the diameter of the pipe, what is happening to your pumping power? Your pumping power is decreased by 16 times. Clear? Right? Your pumping power is decreased by 16 times. So, if you increase the diameter of the pipe, right? If you increase the size of the pipe, your pumping power is reduced. I hope it is clear. So, this is the physical significance of what? Physical significance of our which equation? Hagen-Poiseuille equation for laminar flow. Right? I hope it is clear. Right? So, I hope it is clear. Once again, your pressure drop will be 0 if there is no viscosity. Right? So, based on this, you have different questions in GATE. Right? You have minimum 2 or 3 questions are there in GATE based on the same concept. What they can change? They can change different cases. They can give you a different length, different diameter, different pressure drop accordingly. Right? Everything will be based on this question. Every year in GATE, you can expect minimum 2 questions from that particular internal flow chapter. Right? I hope you're okay with this particular explanation. Thank you.